Alright, class. So last time we started talking about solution and concentration. That we started talking about this in Chem 1. I'm going to continue talking about this. And we said that chemists, they love molarity. Why? We love molarity because chemical reactions are balanced for moles. But not everyone loves molarity, and different people, they have their own units. That's why there are many different units for concentration, and we're stuck having to convert from one unit to another unit. Now, I emailed you guys this chart. So this table shows you some of the units for molarity that are common. The one that chemists love is molarity, of course, but these are other units for concentration that are common and is good to know. So far, so good? Okay. And then we also talked about a stoichiometry. We said, yes, you have to remember the stoichiometry from Chem 1A. Stoichiometry, limiting reagent, mole ratio, you got to remember those. Now, I thought it would be helpful today to do nothing but practice problem to make sure you have those topics down. So I emailed you a practice worksheet. Make sure you work on a practice worksheet before you watch this video. You get so much out of it if you've already attempted it, okay? So make sure you watch the video, you do the worksheet first, and then come back and we can do these problems together. Here is the first problem. When you read this problem, this is a long problem. I also want to show you guys kind of how to approach chemistry problems. So you read this problem, is a really long problem, but that's okay. Don't get overwhelmed. Don't get scared of the problem. Look for things that you could solve. So when I read this problem, it's a long problem, but one thing that stands out to me in this problem is that when I read it, I go, okay, this is not bad. What they've given me, they've given me the volume and they give me the molarity of cerium sulfate. Okay, I was like, okay, I'm going to go based on that before I do anything, because I know that molarity is moles per liter. And in this case, we have the molarity, we have the moles, we have the volume, so I can figure out the moles. All right, what is the molarity? Tell me. It's 0.246 molar. I'm going to put X for moles, and the volume is 15.3 milliliters. But don't forget, molarity is moles per liter. Divided by 1,000, you have to convert it to 2 liters. We're good so far. So what X is going to be is 0.003764 moles of cerium sulfate. Okay, all right, so I have moles of cerium sulfate. I'm going to come back here and I'm actually going to see what does this question ask me for. What this question asked me for, it asked me for percentage of bismuth oxide. It asked me for percentage of bismuth oxide. And remember, percentage is usually mass percent, unless they tell you otherwise. But percentage is usually mass percent. I need you to remember that. That percentage is usually mass percent unless they tell you otherwise. Okay, now remember this. What I found out is moles of cerium sulfate. But what I want is bismuth oxide. This is what I have. This is what I want. We talked about this. Every time they give you one thing, but they ask for something else, what do you have to use? Every time they give you one thing, they give me this, I figure out the moles of this, but what I need is Bi2O3. Every time they give you one thing, but they ask for something else, what do you have to use? You have to use, yes, hashtag mole ratio. It gets a hashtag because it really matters in stoichiometry and in chemistry. Okay, they give you one thing, they give you the cerium sulfate, but what they ask you for is bismuth oxide. So we have to do some sort of mole ratio to get to what we want. Okay, that's great. They give me a balanced equation. I'm going to use that to figure out the mole ratio. Well, oh no, there's a problem. when you look at this balanced equation, there is no cerium sulfate in it, and there is no bismuth oxide in there. So there is no direct mole ratio in here. Do you guys agree? There is no direct mole ratio in here. But I do have two, but I can do an indirect one. So I'm looking at this balance equation, and one thing that stands out to me is that, okay, hold on a second though. They give me the cerium plus 4, and they give me Bi. So I could, not directly, but indirectly, try to use a mole ratio. Okay? So let's see how we're going to do this. So what I'm going to do, the first thing I'm going to do is I'm going to write down what's given to me, what I have, which is 0.003764 moles of cerium sulfate. Okay? Now, I need to somehow get to cerium plus 4. So I don't want moles of cerium sulfate. I don't want the moles of cerium sulfate. What I want is the moles of cerium plus 4. Okay? So what's the mole ratio? What's the mole ratio? Mole ratio is that in one cerium sulfate, how many cerium do you have? Tell me. In one cerium sulfate, you have one cerium. Do you agree? Okay. And I know you know this, but let me go over one more thing with you. It makes me feel better to make sure you really understand and you remember your Chem 1A. So this is CeSO42. So why is this cerium plus 4 and not cerium plus 2? Here is why. I'm going to do a little side note over here. So this is the ionic compound. Ionic compound is balance of charges, right? So what I have Ce and I have SO4. I'm going to write this down. So ionic compound is a balance of charges. Ionic compound is a balance of charges. Okay. Now, I know that SO4 has a charge of -2, and that doesn't change. Okay. Now, cerium has different charges. Now, if it was cerium plus 2, then these two would cancel each other out. Do you guys agree? Okay. And I want to actually write it down because I don't want to assume you follow. Okay. So remember in Chem 1A that we would cross multiply the charges, right? We would cross multiply the charges. Now, after you cross multiply the charges, then you need to simplify if you can. Again, let's go back to Chem 1A. When you have an ionic compound, you cross multiply the charges. The 2 comes here and the 2 comes here. But then if you can, you must simplify. You must simplify. Okay? Now, when you simplify this, what do you get? You get CeSO4. So you must simplify when you can. And we simplify by dividing by 2. So, okay, then it would be CeSO4. That's not what we have. So it's not cerium plus 2. Now, what is this then? Then what if this is a plus 4 charge? If it's a plus 4 charge, I'm going to cross multiply the charges. Ionic compound, I'm going to cross multiply the charges. If I cross multiply the charges, I must simplify if I can, right? I must simplify if I can after that. Now, what can I simplify this to? I can simplify this by dividing by 2. If I divide this by 2, I get CeSO4 2. This is the one that I have. This is the one that I have because I have CeSO4 2. That's what I have. So it's actually cerium plus 4 that I have and not cerium plus 2. You guys follow that? Okay, so the key is to remember when you have ionic compound, you cross multiply the charges, but after that you have to simplify if you can. So what you see, the final product is actually cesium plus 4. 4, not cesium plus 2. All right, thanks for letting me go over that because I just wanted to make sure that everyone's on the same page. So that's why when I have 1 CeSO4 2, that means I have 1 moles of cerium plus 4. All right, so let me erase this because I'm not going to use this. I want to have more room. So hopefully you understand that. And I'm sure you remember it from Chem 1A. So now I have cerium plus 4. And that's good because when I come over here, it's like, okay, at least this is part of the equation now, right? At least this is part of my chemical equation. I can go with that. So I have cerium and I have Bi. So I can do that conversion. I can do that mole conversion. So I'm going to come back here and I'm going to say, I don't want the mole of cerium plus 4. What do I want is a mole of Bi. I want to go to this equation. Remember, I need to remember for me, coefficients are the mole ratio. Coefficients are the mole ratio. What is it? Coefficients are the mole ratio. I can't hear you, but tell me anyway. Coefficients are the mole ratio. So the mole ratio is 3 cerium plus 4 for 1 bismuth. So I'm going to come over here, and then I'm going to put the mole ratio here. Oh, oh my goodness, what am I doing? This is 3 over here. This is 1 over there. Okay. Now, this is great so far because what we've been able to do, we cancel out the moles of cerium sulfate. We cancel out the moles of cerium. Now we have bismuth. We're almost there. Bismuth is not what we want. What do we want? We want bismuth oxide, right? Okay, so the last thing to do, I don't want moles of Bi. What I want is moles of Bi2O3. And for the mole ratio would be in 1 mole of Bi2O3, how many Bi do you have? You have 2 Bi, right? In 1 mole of this, you have 2 Bi. Okay, that's not bad. So what I'm going to end up getting, so that's great. And also, just remember, now the Bi can cancel out. What I end up with is Bi2O3, which is what I want. Again, mole ratio is the key because they can give you one thing, you need another thing. You do mole ratio to get to what you want. Alright, so if you do the math, what you end up getting is 0.0006273 moles of Bi2O3. Now we're in business. So we have the moles of something that we want. Now, remember, what the question asked you was what? The percentage of Bi2O3. So the question asked us for the percentage of Bi2O3. Now, what does that mean? I said percentage is gram percentage. That means the grams of bismuth oxide over the grams of the entire sample times 100%. And I'm gonna go over this too. That if you read this question, this is an impure sample. So this sample is impure, right? You have an impure sample, and they want to ask you in this impure sample, how much of that sample, what is the percentage of bismuth oxide? Is impure, so it has other things in it too. Is an impure sample of bismuth oxide, it has other stuff in it too. They're asking you how much of this impure sample is bismuth oxide. That makes sense? So how much of this impure sample is bismuth oxide? That's what the question is asking us. Okay. Now I told you that I need grams, right? I told you that I need grams because percentage usually means gram percentage unless they tell you otherwise. So that's okay. I have moles. I know how to convert moles to grams. I know how to convert moles to grams. How do you convert moles to grams? You use molecular weight. Okay, so I have moles of bismuth oxide. I use molecular weight. You know that. I don't want the moles. It's going to go down here. What I want is gram. It's going to go on top. Okay, so what I'm going to do, I'm going to use molecular weight to do this. 1 mole is, if you look at periodic table, calculate that. 1 mole of bismuth oxide is 466 grams. So now the moles can cancel out and I can end up with the grams that I want. So the grams that I get is 0.2923 grams of Bi2O3. Alright, I finally have what I want. Now, remember again, we're trying to figure out, there's this sample, how much of that sample is bismuth oxide. So, and we said this is a gram percentage. So I have that. I have the grams of bismuth oxide, so 0.2923 grams over the grams of the entire sample, which I come over here, it was 2.90 gram divided by 2.90 gram times 100. What I end up getting is, and of course we have to care about sig fig. I know sig fig always comes back. 3 sig fig should be my final answer. 10.1%. One thing about sig fig, I want you to remember that this is a good review for Chem 1A. You don't care about sig fig until the very end. If you start rounding off at the early stages, then by the time you get to your final answer is going to be off because you start rounding it up early on. So you don't care about sig fig. You don't do anything for sig fig until the very end. You keep in mind, you go, okay, I know this problem is limited to 3 sig fig, but I'm going to take care of the sig fig at the very end. Because if you do it early on, if you just keep doing it at every stage, your final answer is going to be off. Alright, sounds good? Okay, this was a big practice problem. And the key for this practice problem was remembering mole ratio, right? And I didn't make it easy. I didn't give you an easy mole ratio. It didn't matter. You could use the equation that I give you to get what you want and then go from there. So we made it into cerium plus 4 because this was on the table, this was on the equation, so you can do this mole ratio and then go from there. Alright, great. Ready for the next one? This one took a little long, but that's okay. A solution of NaOH is 35% NaOH. It has a density of 1.39. What is the molarity of this solution? Okay. Now, one thing I need you to remember, and we talked about this before, this is one of the stuff, we didn't go over this as much in Chem 1A. What I need you to remember is that every time you have gram and you want to be converted to milliliters or liters, what can you use? You can use density. Density is a way to go from gram to moles. The same way that if you have gram and you want to go to moles, what do you use? You use molecular weight, right? You look molecular weight, you use molar masses. So just remember that. To go gram to volume density, to go gram to moles, I need molecular weight. And then the best thing to do is to cancel out. That's like your best friend. So what do I got here? I have a solution of NaOH that is 35.0% NaOH, and they give me the density. That's great. They ask for molarity. The first thing I'm going to write down, down here, what am I trying to get to? Remember, what I'm trying to get to is molarity, right? And molarity is moles of solute, which would be NaOH here, over liters of solution. So that's what I'm trying to get to. Keep your eye on this. What is your final destination? I'm trying to get to that. Okay? That's what I'm trying to get. So I'm going to start with what I'm given and try to go to moles of NaOH over liters of solution because they ask for molarity. So the first thing they gave me is 35%. We said percentage is usually a mass percentage unless they tell you otherwise. So if they tell me I have 35% of the solution is NaOH, can I just say that if I have 35 grams of NaOH in 100 grams of solution? Can I say that? Why not? Because percentage is a ratio. So you can make a number to get to that ratio. That means if I have 100 gram solution, 35 grams of that is NaOH. That's how I get 35%. Okay, that's what's given to me. Now, what I want moles of NaOH. What I have is grams of NaOH. So that's not going to work right now. What I want is moles of NaOH. What I have is gram. So gram goes down there and moles of NaOH goes on top. Okay, gram goes down here, so we can cancel out gram. How do I go from gram to moles? Molecular weight. Don't forget that. Molecular weight is always for 1 mole. 1 mole of NaOH is 40.0 grams. Okay, because molecular weight is always for 1 mole. That's great. I have the... Oh, how did I do that? I have the moles of NaOH, and the moles of NaOH is what I wanted on top anyway. Perfect. We're almost there. Now what I need to do, I need liters of solution. What I have here is grams of solution. That's okay. I know how to go from gram to volume. I have to use density, right? I don't want grams is going to go on top, and then milliliters is going to go here. Okay, so then the gram can cancel out. And how do I go from gram to volume? I use density. Density is always for 1 milliliters. 1 milliliters is 1.39 grams. Okay, so I cancel that out. I end up with milliliters, which is what I want. Except here, and this is milliliters of solution, right? We canceling out solution. Except here, they ask you for liters. So the last thing that I need to do is convert milliliters to liters. I don't want milliliters. It's going to go on top, so I can cancel it out. And what I want is liters. Which one is a larger unit? Liters. 1 liter is 1,000 milliliters. Okay, 1 liter is 1,000 milliliters. All right, so that's not bad. I end up with what I wanted. Moles of NaOH over liters of solution. I end up with what I wanted. Okay, now how many sig fig? Ooh, I know you care about sig fig. My 3 sig fig is what I need. So what I end up getting is 2.2 molar. 2.2 molar would be the final answer. Yeah, not bad. One thing I want to emphasize, and it keeps me kind of in shape, make sure that I don't mess up. Always remember that molecular weight is for 1 mole. And the density, that gives you grams for 1 milliliters. Those things a little bit help. Alright, nice job. Are you ready for our next problem? Here is our next problem. It has to do with titration. Now, if you don't completely remember titration from Chem 1A, I do have 2 videos on titration with a lot of practice problems in it. So definitely watch those videos. So every time you have a titration problem, I always ask my students to please draw it out. It really, really helps. Probably you are not as talented as I am in drawing, as you can see, but draw it out anyway. It really, really helps. So we have a titration, we have a burette, and then we have our flask over here to titrate an unknown sample of oxalic acid. So what's in here is oxalic acid. Now, do you remember the formula for oxalic acid? The formula was H2C2O4. It's a diprotic acid. And then over here I have NaOH, okay? And they tell me that the concentration of my NaOH is 0.185. And then what I have to do, I have to add 19.4 ml before the color change, before it reaches the end point, right? End point is when there is a color change. So far, so good. Okay. The titrating that they're asking you, what mass of oxalic acid did you have? So we have some oxalic acid in here that is dissolved in solution, but we want to figure out how much oxalic acid we have in here. So far, so good. Okay. And one more time, the oxalic acid, the formula for oxalic acid. So oxalic acid used to be oxalate. Oxalate is C2O4. C2O4, and every time you have an acid, you have to put an H in front of it, right? Every time you have an acid, you put an H, and an oxalate is C2O4, but C2O4 has a -2 charge, and this one has a +1 charge, so it would end up being H2C2O4. Little review from Chem 1A. So every time you see acid, you're going to put a hydrogen at the beginning, and an oxalic used to be oxalate. You're going to put that down, and then don't forget to balance the charges, because all the acid or ionic compound, you have to balance the charges. Okay, so then this is my oxalic acid. So I have this setup going on. So far, so good. Now, every time you do a titration problem, the first thing that you need to do, you have the molarity of NaOH, and you know how much of NaOH you added to reach the endpoint. Figure out how many moles of NaOH you added. Almost every time we do this, because again, we love moles. We want to figure out how many moles of NaOH did we add. Now remember, we talked about this before. You see molarity, write down the formula. Molarity is moles per liter. And I want to find out how many moles of NaOH has been added to here before you reach the endpoint. I have the molarity and I have the volume, so I'm going to plug it in. The molarity is 0.185. I don't know the moles. The volume is 19.4 milliliters divided by 1,000. I get 0.0194 liters. Okay, so what I end up getting for X, I end up getting, hopefully this is what you got, 0.003589 moles of NaOH. Again, I'm not going to care about sig fig. I'm going to keep all the sig fig until the very end, because if I keep rounding now, my final answer is going to be so wrong. Are we good? Okay, and again, watch my videos on titration if you don't remember titration. I do a lot of practice problems on that. So here's the moles of NaOH that we have. And if you remember, the concept of titration is you're going to add the acid and base together, and the base will go down here. It will neutralize out the acid. Base goes down there, neutralize out the acid. And at some point, when there is no more acid left, when you add the base, that's when there is a color change, because there's a color change when there's a change in pH, right? So here I add NaOH, the acid neutralizes out. I add NaOH, the acid neutralizes out. And then once there is no more acid, if I add NaOH, then it's going to turn pink. Okay, now I added 0.003589 moles of NaOH, and then it changed color. Now, how many moles of the acid did I have here? If this was a monoprotic acid, you would be done, and this would be exactly the same number. But this is a little bit tougher, because this is not a monoprotic acid. Oxalic acid is a diproduct. That means what? So di means 2, product means proton, means H+. That means it has 2 H's. It has 2 H's, okay? So now what does that mean? Here's what this means. I have NaOH and I have oxalic acid, which is H2C2O4. NaOH has one OH, right? One oxalic acid has 2 H+. So one NaOH has one OH, but one oxalic acid has 2 H+. One acid has 2 H+. So for one acid, how many NaOH do I need? I can hear you, 2, right? Because one acid has 2 H+. So for one acid, I would need 2 NaOH. So I can do a mole ratio. So I'm going to come over here, 0.003589 moles of NaOH. Now, I don't want the moles of NaOH. What I want on top is the moles of oxalic acid. So far, so good. Now remember that the moles of NaOH can cancel out. I end up with the moles of oxalic acid. What is my mole ratio here? Remember, for one oxalic acid, to neutralize one oxalic acid, how many NaOH you need? You need 2 NaOH. You need 2 NaOH to neutralize that one oxalic acid. Are we good so far? Okay, so if I do this, what I end up getting is 0.0017945 moles of oxalic acid. I'm almost there. They don't ask you for moles, they ask you for mass. How do you go from moles to mass? You know that, molecular weight. So 0.0017945 moles of the oxalic acid. Again, I have to go from moles to grams. I just use molecular weight. 1 mole of oxalic acid. Oh, what did I just do? Just testing out and making sure you're paying attention. 1 mole of oxalic acid is 126 grams. Oh, I even give you the molecular weight. Look at that. I'm getting soft. So moles can cancel out. What I end up with is grams. So what I would end up with is 0.226 grams, because we do have to care about sig fig. My final answer should have 3 sig fig. Yeah, not too bad. Okay, now I want to go over one more thing with you. So hopefully you understood what I did here. Now, if you're having a hard time to understand that, or sometimes the ratios are a little bit harder to figure out, if I have a base that has like 2 OH and I have an acid that has 3 H. If you understand this is great. That for 1 mole of oxalic acid, you need 2 NaOH, because 1 NaOH has 1 OH. 1 oxalic acid has 2, so I need 2 of these to neutralize that 1. Yeah? Okay. So hopefully you got this down. Now, if you don't, there's another way to do this. And the other way to do this is to do a double replacement reaction. Because what we have, and I want to go over that in case you're having a hard time with that. What we have here, we have adding NaOH. Let me see. Let me have a thinner pen. We have an NaOH. We have our, hold on. What's going on here? There we go. We have NaOH, which been added to oxalic acid. Okay. Remember the double replacement reaction in the good old days? Inis with inis, outies with outies, right? Inis with inis goes outies with outies. So I end up with sodium and then C2O4, but don't forget you have to balance the charges, right? You balance the charges. This is +1, this is -2, so you have to balance the charges. So I get Na2 C2O4 plus. Now OH goes with H plus. What is OH plus H plus? Do not tell me it's HOH. That's a little ghetto. That would be H2O, right? Yeah, you know that. Don't say it's HOH, it's H2O. And every time you have an acid-base reaction, water is a product. Every time you have an acid-base reaction, water is a product. I want you to remember that. So this is our double replacement acid-base reaction. Now we are going to balance it out. I have 2 sodium here, so I'm going to add a 2 over here. And then I'm going to add a 2 over here. Okay. Now that I have a balanced reaction, you see that the mole ratio between sodium hydroxide and oxalic acid is 2:1. And that's what I used over here. So again, I wanted to show you both ways to make sure that you know it both ways. So far, so good? All right, ready for the last problem? Let's do this. Oh, okay, so to react, that's I think supposed to be exactly. Exactly. There we go. So I have 50.0 milliliters of barium hydroxide solution. Reacts exactly with 40.0 milliliters of phosphoric acid, producing. There we go. Producing 3.00 grams of barium phosphate. What is the initial molarity of phosphoric acid? Okay, so when I look at this question, again, like I said, don't get nervous by any question. Don't be scared of them. When I look at this question, I was like, okay, this is stoichiometry. That's good. And then this is a hard question. I have barium hydroxide and I have phosphoric acid. So what kind of question is this? I have a base and I have an acid, right? I actually have an acid-base reaction here. And then so you have 50 ml of barium hydroxide that is going to react exactly with 40 ml of phosphoric acid, and it forms 3 grams of barium phosphate. So when I look at this, I go, okay, probably what I need to do is to have a balanced reaction. Do you agree? Probably what I need to do is to have a balanced reaction. So let's do that first. What I have is, I have barium hydroxide. Sometimes they give it to you, sometimes they don't give you balanced reaction. I usually give it to you on exam, but this is a take home, so it's good for you to practice. So here is an acid-base double replacement reaction. Acid-base double replacement reaction. The same as before. In is with in is, out is with out is. Definitely make sure you reviewed it from Chem 1A. So barium is going to be with phosphate. Don't forget the charge on barium is plus 2. The charge on phosphate is minus 3. So if I cross multiply the charges, this is a 3, and let me see. If I cross multiply the charges, I get Ba3, PO4, 2. You guys are good so far? Okay. And even if you didn't remember that barium was plus 2, phosphate was minus 3, you can figure it out from here. You know OH is minus 1, so the 2 had to come from barium. You know H plus is always plus 1, so the 3 has to come from phosphate. Okay, so you can use this to figure out the charges if you do not remember your polyatomic ions and the other charges. All right, then H goes with OH. We talked about this. What is H plus OH? H plus OH is water, which is really cool because what is the pH of water? The pH of water is neutral. Why is it water neutral? Next time when you're drinking water, I want you to be thinking about this. Why is this water neutral? And you can answer yourself by saying, because water is made from acid and is made from base. That's what is neutral. It's really cool. All right, so we got this down. Now the question is, we need to balance it, right? We definitely need to balance it. How would I balance this reaction? I have 3 barium over there, so I'm going to add a 3 over here. I'm going to add a 2 over here and 6 over there. I'm not going to go over balancing reaction. You notice by now pretty well, I'm sure. Okay, so here's our balanced reaction, okay? Here's our balanced reaction. Let me erase this so it's just easier to see. Here's our balanced reaction. Now let's read the problem and then do this problem. So what you have 50 ml of barium hydroxide. So I have 50.0 ml of this and reacts exactly with 40 ml of phosphoric acid, okay? And what is formed, 3.00 grams of barium phosphate is formed, okay? Now the question is, what was the initial molarity of the phosphoric acid? I want to make sure you really understand the question. So you're going to add these two solutions together and it's exact amount. So basically, I'm going to add barium hydroxide to enough phosphoric acid that every single one is going to react and is going to form barium phosphate. As it says, to react exactly. So then I don't want to have any leftover, okay? We want to have basically, that's what I say, exactly, because that means no leftovers. I don't want to have any leftover, no excess reagent. I just want every single one to react. So far, so good? Okay, so that's what that exact part means. Now, what is molarity again? They're asking you for the initial molarity. And the first thing I'm going to do, and we've done this so many times, I'm going to write down that I know molarity is moles per liter. And that's what they're asking you for. They're asking you for moles per liter. Okay? Now, guess what? You already know the liters for phosphoric acid. The liters is 40 ml divided by 1,000. That will give me the liters. So you already know this, okay? You're trying to figure out the molarity, which means you need the moles. So you somehow need the moles to figure this out, okay? Okay, let's figure it out. Now, the only piece of information they've given us, minus the volume, is a grams of barium sulfate, some phosphate. So I'm going to start with that. I have 3.00 grams of barium phosphate. Now, keep in mind for me again, what you want, what you need is what? What you need is moles of phosphoric acid. I need you to really remember that what you need is moles of phosphoric acid. Now, check this out again. They give you one thing, they ask for something else. What you need is a moles of phosphoric acid. What they're giving you is a grams of barium phosphate. Okay? So, what do I have to do? I can almost hear you guys. They give me one thing, but they ask for something else. So I have to use hashtag mole ratio, right? So we have to do hashtag mole ratio because again, they give me one thing, they give me this, but I need the moles of phosphoric acid. So I have to do hashtag mole ratio. That is our thing. I'm actually going to write it down too. So I have to use hashtag mole ratio because they give me one thing, they ask for something else. Before I can do mole ratio, I need to convert grams to moles. So 1 mole of barium phosphate, I even give you the molecular weight, I've gotten soft, is 601 grams, okay? So then the molecular weight the gram can cancel out, okay? So I had gram to go gram to moles, I need molecular weight. Molecular weight is always for 1 mole. That's great. Now, I don't need the moles of barium phosphate. I don't need the moles of barium phosphate. What I need is the moles of phosphoric acid. So what I need is the moles of phosphoric acid. Coefficients are the mole ratio. Coefficients are the mole ratio. Coefficients are the mole ratio, right? What is my mole ratio here? I have 2 phosphoric acid for 1. I have 2 phosphoric acid for 1 barium phosphate. So I use a mole ratio. Coefficients are the mole ratio. Coefficients are the mole ratio. Okay, this is great because now moles of barium phosphate cancels out and I end up with moles of phosphoric acid, which is what I want. Okay, so what that is 9.983 times 10 to the minus third moles of phosphoric acid. Beautiful. Okay, so now we are back in business. So remember, I needed to figure out the molarity of phosphoric acid. Yes? Do I have the moles of phosphoric acid now? I sure do. Is 9.983 times 10 to the minus 3. Do I have the volume? We always had the volume because the volume was 40 ml. Divided by 1,000 because you need it in liter, that would be 0.0400 liter. So if I do this, what I end up getting is, how many sig fig? 3 sig fig. Pay attention to sig fig at the end, 0.250 molar. That is my final answer. Sounds good? Okay. And the only thing that was a little bit hard about this problem to me is just figuring out what does exactly mean. Basically what that means is there is no leftover, right? There is no excess reagent, there is no leftover. Every single one is going to react with every single barium hydroxide and phosphoric acid is going to be neutralized out. Sounds good? Okay, so we did a lot. We did stoichiometry, we did lots of mole ratio, we did titration, we did molarity, converting. So hopefully you have a good grasp on the concept now. I will talk to you guys next time. Thanks for hanging in there with me.